So for today, the plan is to go through this whole problem set since it's actually due before the exam. And I think that the material covered here will show is part of the exam. Well, I haven't cross-referenced like the section numbers. Um, so next recitation is supposed to be a review, and I think what I'm going to do is I will send out a link to a Google form that you can fill in, like where you write down like what you want me to cover, like topic wise, or if you have like specific problems. So there's one thing that I kind of need to show. I guess I'll show my whole screen. So there's an exam archive for math. All you need to do is just Google KSU Math Exam Archive, and then you'll get access to this. And if you just fill in what is the course we're in, so this is calculus, Calc 1, you can then take a look at, I would say, so this is the spring semester, so probably the exam ones from the spring semester are the most relevant, and you can kind of get a sense of what the exam is supposed to will most likely look like. The version or the style of the exam doesn't really change too much between semesters unless you go like way back. So you can use this in order to try practicing a little bit. And otherwise, like I could try to find problems from the textbook or other things, but it would help out if you let me know like what you want me to work, what you want me to focus on, and then I'll I guess plan something out. So I'll send that link sometime later today for people to fill in. But yeah, so hopefully you can. It's not exactly very organized this, but you can kind of tell like so the F means fall and then S means spring, and yeah, so like this is another version. This one's a little bit different. You'd want to find one that's, or you could just try the fall ones also. It shouldn't make too much difference. Yeah. Okay. Anyway, let's come back to. Let's come back to the problem set. Right. So, you guys learned about the derivative of the exponential function, the logarithm function, and the inverse trig functions. So those are all a bunch of various rules that we can quickly review. Let's see if this is written in any nice way. Okay. Oh man, how do I want to do this? Well, okay, first let me just, I guess, flash this onto the screen. So these are in the slides. And what I want to mention is these logarithm properties. So you should be comfortable with these logarithm properties. There's a technique that you learn, which is used in number 4, and I think just number 4, logarithmic differentiation, where you really need to actually be able to simplify these logarithm expressions. So multiplication inside a logarithm will split into addition, and division splits into subtraction, and exponentiation, you can pull the exponential out. And that's pretty much all this is. Well, this here is saying that the logarithm and the exponential function are inverse functions. So when you apply one and then apply the other, you cancel things out. And you can do that in either order. Don't really need that. And I think that it's better for me to just write the rules out. It's funny that yeah. Yeah, so I'll just go ahead and write the rules out. Okay. pretty busy day for us. Right. So the first thing is that if you have the typical logarithm function and you're taking its derivative, you just get 1 over x. If you have ln with respect to just some base, some arbitrary base, so you might normally see this not as ln b, actually. You would see this as log base b. And I see that there's a little message here. We can work on it Thursday through Monday. Does that mean you just print it out? It says take home. I think yes. I didn't check the actual dates, but yeah, it runs over multiple days, and yeah, it's considered to be take home, so you can spend some time on it, and you're just supposed to upload it onto CrowdMark, and we will end up grading it. Yeah. I don't remember the details of in the announcement, but it's all in the announcement or the whatever he sent out. Yeah. Okay. So now if you have a derivative, if you're taking the derivative of just an arbitrary log function, not over base e as this natural log is, but over some arbitrary base, you still have a 1 over x, but you have a correction factor. You have ln of b, 1 over ln of b. And actually, one way you can think about this is that this is actually due to the base change formula, because you can actually rewrite this as the base change formula says you can rewrite this as any log of x over any log of b. So I can actually rephrase this as the natural log of x over the natural log of b, and then from that you can see that the derivative would give you that. Another thing is the exponential functions. So e to the x, you should know that it has a very easy derivative. It's just the original function. If, however, you have over an arbitrary base, so here, well, normally I use a to the x, then the derivative of this function is going to be a to the x with a correction factor of ln of a, right? Just some number. And you'll notice that like these two derivative rules are more general versions of these other rules, because you should remember that ln of e is equal to 1. So that's how these more general formulas will simplify. Okay. And we learned chain rules, so hopefully you're comfortable enough with chain rule. So there's one thing that I maybe should mention about this. So when you are taking the derivative here, there is actually a chain rule that will take place. So when you take the derivative, this is just something a little bit different. So the derivative of the exponential function would give you the exponential function, but then you have to take the derivative of the inner function, which is the 7x. So there's a chain rule that takes place. So you get this as your final answer. This shows up in, I think, the very first problem. Okay. And then the next thing I want to go over is the inverse trig functions, the formulas for those. So I'm going to, should I abbreviate? Well, I guess I can just do that. Sine inverse of x has the derivative 1 over the square root of 1 minus x squared. So that is the derivative of inverse sine, and then inverse cosine is easy enough. You just put a negative in front. Inverse tangent looks slightly different. 1 over x squared plus 1. Some people switch those two and they say 1 plus x squared, but here it doesn't make a difference. We have cotangent inverse. Also, it just has a negative in front. And then secant and cosecant, I don't think you need to memorize them, but at some point you it is assumed that you know it. So -1. So this is absolute value of x times the square root of x squared minus 1. And then cosecant is, you see the pattern. You put a negative in front. Square root of x squared minus 1. And just like how the derivatives of the trig functions sort of divided up into families, the inverse trig functions also will divide into families, like so. And typically we just ask that you remember inverse sine and inverse tangent. But I mean, it's not so hard to remember the rest of them. Okay. Any questions on this or on material from the lecture? No? Okay. Then let's go ahead and get through these problems. Right, so we go through this term by term. And this first one, you should know that, well, the derivative of the exponential is just the exponential, but there is an inner function, so we have a chain rule. So you could write this as times 5, or you could write this as like 5 in the front. I'm going to put it as 5 in the front just because I would normally be able to see, to look ahead and realize that the 5 should actually go in the front. Okay. This is a general exponential, right? Your base is not e in this case, so you know that you've got that little correction term. So the correction term pops out. You have an ln of 7. You normally like to put that in parentheses just to remind myself that that's a number. And so then you've got the 7 to the x because it's an exponential function. Okay. Now this one is a little bit trickier. We have an inverse tangent function, arctangent. And so you have to remember the way that that formula works. You do 1 over and then 1 plus, and then the quantity gets squared. So this whole function inside is going to get squared. But then also you notice that, well, this is an inner function, so you have a chain rule that takes place. Okay, so altogether, what we are going to have to do is we say 1 plus and then 3x to the 7 plus 4x. We square that whole quantity, and then we multiply. I may as well multiply it on the top of the fraction instead of off to the side, just save a bit of space. And so we now take the derivative of this inner function, and that is just power rules, right? So this is going to become a 21x to the 6, and then that term is going to become a 4. Then you can just leave it like that. For part B, you should see that this is a product rule because it's a product of two different functions. The easier function to take the derivative of is this exponential, so we may as well think of that first. Right? So if I take the derivative of the exponential, I'm just going to have e to the t, and then we copy down the other guy. Okay, so it looks like nothing happened. But now we have the second half of the product rule, which says we need to take the derivative of the other guy and just copy down the other function. Okay, so now taking the derivative of inverse sine, and notice that this inner function is a bit more complicated, so we have a chain rule that will take place. Okay, so derivative of inverse sine is 1 over the square root of 1 minus, and then it's the quantity inside squared. So we have this inside. So this gets squared, so we end up squaring t cubed, which is going to give me t to the 6. Okay, and the product rule, or not product, the chain rule is going to say we then also take the derivative of t cubed, which will be 3t squared. Okay. Any questions on that? Did everyone follow? Okay, one thumbs up. Fine. Okay. C. Well, C. You can tell that this has a quotient, or this has a quotient rule because it's a quotient of two functions. One thing should I do it that way or not? Let me think. Yeah, it's slightly better to do it this way. So there's a simplification you can do here, which if you remember your log properties, you remember that you can actually pull the exponent out. So I would rewrite this as 2 ln of w. And the reason I do that is because I want to save myself from doing a chain rule inside of a quotient rule. Okay. So when we get to that, we will take the derivative of this, and that's going to be easier. Now let's go ahead and do quotient rule. So quotient rule says, and hopefully remember it, but I guess just in case, I will write it off to the side. Du prime minus ud prime over d squared. And so we have the tangent function times the derivative of the numerator, which is going to be fairly large. And so now I need to take the derivative of this. So that's going to be 2 over w. And then plus, okay, so now we have this term, and this is a log function, but over a different base than the natural log. So we know that we have a little correction term here, and then times 1 over w. And so this ends up being the first half of quotient rule. Second half says copy down the numerator times derivative of the denominator. Okay, so just copy down. Okay, log 2 of w. And then derivative of tangent, hopefully you can recall, this is secant squared. And this is all over denominator squared. So this is going to be over tangent squared w. Okay. Part D, this is a very typical type of problem to do. You've got these nested ln's. All right, so you should remember that the derivative of ln is 1 over x, right? But that is if the ln function just has inside of it x, right? In this case, you've got like ln of something. It might be easier to do a simpler version of this problem. So ln of x. Okay, so what happens is there's going to be chain rule, obviously, because we have a function stuck inside another function, right? The first thing that we would do is we would take the derivative of the outermost ln function. That's going to turn into a 1 over x, or sort of a reciprocating function. But remember that the chain rule says we actually need to plug the inner function back in. So we actually get 1 over ln of x. That is the derivative of the outer guy. And then we say tack on the chain rule piece, which says take the derivative of the inner function. Then the inner function is going to be 1 over x. So this ends up being the full derivative for this expression. Okay. And to generalize this to have 3 or however many you want, you just go ahead and do the same exact thing. So when we take the derivative of the outermost ln function, that's going to reciprocate everything inside of it. You have ln of x, and then, well, derivative of this inner function, which is actually this guy in the denominator here. That's going to be 1 over ln of x, and then derivative of the inner function, which is this ln of x function, is going to be 1 over x. So we have this, and that's our answer. Okay. Any questions on this number 1, all of these parts? No. Okay. Now let's keep going. Okay. So we have a headed function, and we're asked how fast is the plane rising 5 minutes after takeoff. Right. So this is actually asking us to find h prime of 5. Right. So we just need to take the derivative of this function, and then we plug 5 in. So let's start by taking the derivative. So the ln function is just going to reciprocate. So I kind of know that the 3500, I can put that in the numerator. And then we have a t plus 1. Okay. And you could do a chain rule, but that's just going to give you 1 back as a function. So this is the derivative. And then we just plug in. So 3500 over 6, which simplifies a little bit. 1750 over 3, and that's approximately 583.33. And you should always put units if you're given units. So feet per minute. Okay, and you can, I don't know, box one of these, I guess. All right, so that's not so bad, I think. For number 3, well, you definitely need to use a calculator for this because the decimal values are pretty bad. Find and interpret the meaning. Okay, so that's kind of like the stuff from the last problem set. Okay, so, but I think it's pretty clear. You just plug 0 in and you're going to get something. In this case, the numerator, for 0, you can actually calculate this by hand because you see that the exponential becomes e to the 0, which is 1. So you get this. And reading the way the problem is phrased, you see that this is given to you in terms of thousands and years from 1960. So this is saying that you've got 5,300 cases of influenza in New York City in 1960. So that's what this statement is saying. And if you calculate n of 4, again, this is you just plug it into a calculator, you'll get approximately this. And so in terms of this being thousands, this is actually 723 cases of influenza in New York City in 1964. Okay. So that's relatively straightforward. For the part B, we actually need to calculate n prime, which we should do by hand, and then plug in, which we should do by calculator. So n prime of t is going to be, I think I can just, write it like this. So this is an exponential function, and you have this inner function, which is a polynomial. You can take the derivative of a polynomial pretty easily. And the exponential you would just copy down. So you see that the only thing that happens is that there's like a chain rule that occurs. So 0.93t squared minus 0.87t, and then you've got the chain rule. So when you take the derivative, you still get all of this, and then you have the chain rule at the end. So this is going to give you, what's that number? 0.186, just double that, t, and then minus 0.87. Okay. So this is now your function for n prime that you're going to actually plug things into. Okay, so n prime of 0 is going to give you negative 4.611. Maybe I'll also just write down what n prime of 4 will give you. Negative 0.0911. And I think I forgot to turn this into thousands, didn't I? Okay, so when I did this, all right, yeah. So yeah, when you convert this, so understand that the units of this is actually thousands of cases of influenza, right? So I still need to, when I turn this into words, I still need to multiply 1,000. So and this is saying something about the rate of change. So rate of change of the number of cases, kind of change things, the phrasing. So what I ended up writing is that the number of influenza cases in New York City in 1960 is decreasing at a rate of, and okay, I see what I wrote down. Okay, yeah, 1, 2, 3, yeah, okay, 4,611 cases per year. So it's decreasing at this rate. And then similarly, you can translate this statement. Maybe I'll just say like, yeah, same thing. In 1964 is decreasing at a rate of And then this is 91 cases per year. Okay. Any questions on that? No? Okay. Fine. Then we have number 4. And I don't know, if we have extra time, then maybe we can do a little bit of exam prep if you guys have any questions in mind, anything that you want us to go over. So logarithmic differentiation though. Let me see, how thoroughly did you guys cover this in the slides? So you take a log, you take the derivative. Yeah, I think that should be fine. So did you do the typical problem? Not sure. Okay, well, let me know if you get confused by this process. But so overall, there's two ways that you can sort of realize that you should use logarithmic differentiation, not just because like you're told to, but two ways that it can happen in practice. And these two functions sort of are the two different cases. The first case is where you have the variable that is changing, in this case x, in both the base and the exponent, right? So I guess this is just a quick little side comment. So if you have like, uh-oh, my writing is disappearing. That's not good. Right, so if you have the variable in the exponent, you know that this is an exponential. If you have the variable in the base, you know that this is a power function, and you just use power rule. But if you have both the variable in the base and the exponent, you're kind of stuck. You kind of shouldn't use either of the rules because it doesn't completely match. And so in this situation, x to the x is the easiest example of this. You have to use the this process of logarithmic differentiation. And what it does is it lets you lower that exponent. So what you normally do is you wrap the function around it. Well, normally what you do is you call it something new. So you call it something like y, and then you just say apply the natural log function to the whole thing. That's so it may be slightly better to do is to like say I draw an arrow and I say ln, and then that means I'm applying the natural log function to both sides of this equation. Okay, ln of x to the x. And then what you should remember is the certain log properties allows you to pull this exponent out. So we have x ln of x. And now what we have is a product of two functions. So we can use product rule. So we are able to actually take the derivative of this equation. Now, this is something that it's actually in a section that you haven't covered yet. This is what's it called? Implicit differentiation. So I guess we're sort of going through things a little bit out of order, but the derivative of this ln of y is not just 1 over y in this case, but it's 1 over y times y prime. 1 over y times y prime. There's actually a chain rule. And the reason for that is that this derivative is actually a derivative with respect to x, and y is actually a function of x. In a way, you're supposed to think of y as a function of x. So if we're just trying to take the derivative of some function called y, take the derivative with respect to x, it's not just going to be 1 over y, because the inner functions, this y function is actually slightly more complicated, and so you have a y prime attached as well. And then the right hand side, you can do just an ordinary derivative, and that's going to give you ln of x plus x over x, so that's just 1. And then what we normally tell you have to do is you have to bring this y 1 over y to the other side, multiplying both sides by y in order to isolate the y prime. The y prime is the derivative that you're actually originally looking for. So for this typical problem, you get this as your answer. And this is the easiest example I could give you on how logarithmic differentiation works for this case. Okay. And then I want to say just a quick thing about this one. So notice how complicated this is. Notice that because you have a quotient, you have powers, you have a product, you have to use all of the rules that we've taught you, the quotient rule, the product rule, the power rules, and it's going to get pretty messy. But here, this is where taking the logarithm is helpful in another way, because it helps to simplify the function, right? The logarithm is going to turn that product into addition. It's going to turn the exponentiation into just scalar multiplication. It's going to turn the division into subtraction. So you end up getting a much simpler function when you take the logarithm. And that simpler function is very easy to take the derivative of. That's the other case where you might want to use this process of logarithmic differentiation, is when you have something that has a whole bunch of things being multiplied and divided, and it can just yeah, help in that way. But okay, now I think I've said enough, and let's go ahead and just calculate this. So the first thing that I will want to do is I will want to call the function that we're actually taking the derivative of something. So in Craig's slides, I think he calls it like f of x. I normally just like to use y. Okay, so we've done that, and then what we have to do is we have to take a logarithm of both sides of the equation. So that's going to pop the exponent out. And so we get this, and now we can take the derivative. So I'm just doing an arrow indicating derivative, and we get 1 over y prime is equal to, and then here I've got a product rule. So this is going to be 2 cosine x ln x plus 2 sine x over x. Okay, and now the final step is you just bring this 1 over y to the other side by multiplying. And you recall that y is what we defined above. So it's this x to the 2 sine x. It's this original function. And this ends up being multiplied by everything that we wrote down from the right-hand side. So we can just copy all of this down, and that's it. And we can box this guy. Okay. All right. For part B, well, same kind of thing, but this time it gives you what f is, so, or it gives the function a name. So I'm just going to use the same name, and we're just going to take the logarithm of this function now. Okay, so we take the log of the left-hand side. That doesn't do anything. Right-hand side, lots of simplification happens. So this is where I would like to say that you should be able to just do the full expansion just in one fell swoop. But if you're not comfortable with it, then practicing is a good idea. And the where's that algebra thing that this algebra textbook can be helpful for that. Right. So remember, it's going to turn this division, subtraction, this multiplication is going to turn into addition. These exponentiations or these powers get pulled down, and then this e is actually interesting. Ln of e is 1, so they're going to cancel each other, and you're just going to be left with a 3x squared. So we'll have a 3x squared as my first term. My next thing is going to be 7 ln of 92x plus 3, and then minus 3 ln of 9x to the 6 plus 5x squared. Right. So I'm doing a few steps in my mentally, just yeah, you apply log to the whole expression, and then you just go through the various transformations that expand it all out. And this is what you'll get. And then you just now we can take the derivative. So for this, maybe these extra set of parentheses might help to see what's going on for that. So we have 1 over f of x times f prime of x for the left-hand side. For the right-hand side, we have, let's see, 6x plus 7 times 92. Sorry, I did that a little out of order. I was preempting the chain rule. So let me 7 over 92x plus 3 times and then chain rule, right? Because I have to take the derivative of the inner function. That's going to give me a 92. And then minus, and now here, 3 over 9x to the 6 plus 5x squared. And this is going to be multiplied by the derivative of the inner function, which is this polynomial. That's going to give me a 54x to the 5th plus 10x, I think. Right. The last step is the annoying one where you just have a lot of hand movement, but nothing else. You should always sub back in the original function. So you shouldn't just write f of x, but you should actually copy down what it is. Oh, whoops. 9x to the 6 plus 5x squared raised to the 3rd. And then this is all being multiplied by all 3 terms here. You, on an easier problem, maybe there'd be some simplification here that would just save all the handwriting, but here I basically just have to copy it all down again. Yeah. And I wouldn't bother calculating any of these numbers. It's just doesn't seem worth it. Oh, X. Yeah. And then of course close off that big set of parentheses. And so that's it. Yeah. Any questions? This or exam material, we can start going over things. No questions? Okay, well, I guess I'll stop recording.